In this video, I will derive the relationships for true stress and true strain. Okay, so for true stress, the relationship is equal to true stress is equal to engineering stress multiplied by 1 plus the engineering strain. So how we can derive this equation? Uh, so we can look at the definition of the stress. So for example, the engineering stress is equal to force divided by the original area, and by the same analogy we can say that the true stress should be equal to the force divided by the current area, or you can also say that instantaneous area. Okay, so considering these two definitions and then adding one assumption, the assumption is that when we apply the stress on a body and then that body goes under the plastic deformation, there is a constant, the volume of the body remains constant. So for example, just to explain like this, so for example, if this is the stress strain curve, so this is the stress strain curve of a maybe say steel bar, and then there is this stress strain curve for the steel bar also. Okay, so this stress strain curve, there is the difference between these two curves. So one is this curve is the engineering is for the engineering stress, and this is for the true stress. So the curve for true stress is normally higher than the engineering stress, because beyond the elastic limit, the area, the cross-sectional area of the specimen decreases. So therefore the true stress will be more than the engineering stress. So the assumption is that the volume remains constant. Okay, so this assumption is very much true. So for when the volume is constant, so then we can write that A naught times L naught is equal to AI times Li. So A naught is the original area, L naught is the original length. So original area times original length is the volume, and then AI is the current area and the current length. So their product is also equal to volume. So from here we can write that A naught divided by AI will be equal to Li divided by L naught, or in another way, Li is equal to L naught plus change in length divided by L naught, or in another way, L naught over L naught is 1, and then it will be delta L plus L naught. But delta L plus L naught is equal to the engineering strain, so it will be equal to 1 plus epsilon. So we can say that A naught over AI is equal to 1 plus F. So remember this equation. Okay, now I go to this equation. Okay, this one, true stress equation, which is the definition of the true stress. So force divided by AI. So from here maybe okay, what we can do is I can take AI from here. So if I take AI from here, so AI will be equal to so from this equation, okay, AI will be equal to A naught, AY will be equal to A naught over 1 plus epsilon. Okay, so if I input over here A naught divided by 1 plus epsilon, so if I simplify it, so then it will be F over A naught times 1 plus epsilon, And what is F over A naught? F over A naught is the engineering stress. So true stress is equal to F over A naught engineering stress multiplied by epsilon. So here we have derived the equation for the true stress. Now we can derive the equation for true strain. Okay, so true strain is different from the engineering strain in a way that in the engineering strain, for example, if you see that we take the change in length and we divide it with the original length. In this situation, you can see that original length remains constant. So whether the change in length is one value or another value. But for the true strain, the change in length and the length to which it is divided will both change. Okay, so there will be a true strain, what we call as a first true strain. Okay, for example, that can be written as change in length, okay, divided by the uh, original length. Okay, that is the at the first moment. Okay, and then you can take another true strain as some change in length, but in this case this true strain will be taken with respect to the new length. Okay, so the length on which that strain will be based will change anyway. So for generally speaking, if you take any increment of the strain, so we can represent it as d epsilon t. That increment of the strain will be equal to the increment in the length divided uh, by the length at that time. Okay, so that will be the incremental strain. So the overall strain from length L naught to Li will be the total strain. Okay, so the total strain d epsilon t will be equal to uh, from 0 to the final strain value. Then this will be equal to the dl over L from length L0 to Li. So we will need to take integration for this to find the total strain. So these are the definite integrals. So this will be equal to et minus 0 epsilon t, and this will be equal to, because L is in the denominator, this integral is natural log of L, but its limits are Li and L naught. So log Li minus log L naught, which is equal to log Li over L naught. And then we know that Li over L naught is equal to L plus change in length, L naught plus change in length divided by L naught, and then natural log, so it is equal to 1 plus epsilon, because L naught over L naught is 1, delta L over L naught is the engineering strain. So this is the equation for the true strain. Okay, so this is how we can derive the equation for true strain.